Alright, if you're me, it's been approximately 30 seconds since the last video. If you're not me, it's been an indeterminate amount of time, and I suppose I would have to do some I/O operations to get your exact time and then calculate the difference. But I don't think I'm going to do that, and I feel like that would probably involve some hacking, and so, just not very ethical. So, anyways, we have went through functors. I highly encourage you to go through the first video about functors. Maybe you just tagged along for this video because you are interested about applicatives, and be your own, control. Maybe you've learned about functors very well in the past, and you just want to learn about applicatives now. But if not, you definitely want to learn about about functors before applicatives. And also, assuming that my spiel at the beginning of that video had any value, I think you want to hear such a spiel about why functor, applicative, and monad are all kind of the same. Same jive. And yeah. So anyways. So applicative. So what is a applicative? Well, I do not know what a... Never mind. Bad joke. And I wasn't sure how to deliver that one. So I'm just going to cut it there. But let's start on what applicative is. So applicative is a superclass of functor, and as we can see, it still has the same constraint. And so, if it's written in this way, and I guess this also tells us the exact same thing, in that an applicative is something that is a type constructor awaiting one more type to become a fully applied real type. Yeah. And so why that is, just to really hit that home, is to is so that the type class and the functions that it has apply to like wrapper types. So example number 1, identity is a functor, applicative, and monad. Non-example number 1, int is not, because int does not wrap anything. Maybe is a functor because just it will, maybe has the ability to wrap a function, to wrap a value, and that makes sense when we look at the data type of maybe, or the data declaration of maybe rather, where we can have just a or nothing. And we talked briefly about how maybe is more complex than identity, and because it has nothing. And so in the case of nothing, we do the what makes sense in terms of maybe, and that's just continue to give back nothing. And then either is very similar to maybe, and yeah, I guess that's a good recap. So now if we look at applicative, so there's there's 3 core functions that really matter here. Everything with applicative is actually pretty useful, I would say. I actually do genuinely use all of these functions and more that are kind of defined off of this function. But the core functions here, I would say, are these 2. And we're also going to just forget about this one for now, and we're just going to focus on this one, because this is really like, a bigger F-map. Or not a bigger F-map, but like it's very F-map-like. So, come on. So we had fmap here, and we also have this function. And so what is the difference between the two? And we kind of applied that to make an example. But there's only literally one difference between them. Only a singular difference between them. And, you know, we don't have our applicative constraint in here. It is technically there, but for the sake of, well, you know, I guess I can also just push this forward more. Yeah, geometry. And so, and I guess this is even, but now we're just getting away from stuff. I'm assuming, you know, I'm very much relying on the fact that you've watched or learned about functors before and can just follow along with this video, because otherwise I don't know what to do here. So the only difference here is literally that this f is now in front of our a to b. And so we still have an fa, and we're still going to return an fb, but we also have this wrapped a to b. And so our function is now wrapped instead of being out in plain sight. So what does this mean in principle? Well, we could have just +1 applicative function, just 2. And then we end up with just 3. So that's really it. You know, we could also have, we could change this to, and this is the inline function for fmap. So I'll introduce that just so you guys can see that. But this is the exact same thing as fmap. It literally just inline fmap. But yeah, anyways. The only difference is that our function is now wrapped. Yeah, that's really all there is to say. And just for the sake of it, I am going to write. Now, in the past, I've written the applicative instances for, you know, identity, maybe, and either when doing demonstrations, but I don't think that's even necessary. I mean, I could do that, and yeah, I could do that. And if I get comments saying that someone would like to see that, then I can absolutely do that in another video. But yeah, I don't think that's even necessary. So I'm just gonna jump right to either, and so we have instance either a, instance applicative either a, where fmap, or pardon me, yeah, why am I blanking out? We have how would I write this? I would do, oh, what am I saying? Sorry. I am trying to make this more general than I need to. But in this case, in this instance, I know that it is right. Yeah. So, let's see. Oh, and we do have actually a bit more complexity, come to think of it. And we see that in terms of how we apply this. So we have write f, and then write x. So, all we're doing is applying f to x. So we're going to say write, first we're going to spell it correctly, and then write wrapping the result of fx. And that's just really, that's kind of the same thing. The only difference is we've wrapped the function now. We have a second case here of what about in the, get my types mixed up. So we have to enumerate through we have to make sure we cover all of the cases in order to write the valid instance. And so if we have left E, then what would we do here? So it would be invalid, just like with functor, to apply how we had this here. And actually, I don't need to comment that out. What? Where's that parser coming from? Oh, is that it? I suppose I can look at the line. Oh, because okay, that makes sense. What happens? Can I compile this? Doing this because I have no implicit prelude. Man, make me do everything. Oh, yeah. Okay, cool. So I actually kind of gave a little sneak peek to what we're going to do next, but we're not there yet. So now in the case of, so we saw with fmap that we would just return the left E, and there was no point in trying to apply F to E because that's just simply invalid. And we could even have a, maybe, I'm not really sure. I do encourage you to I do encourage you to try seeing what would happen if you had like an either with an A here instead of the B, and then seeing if you could apply F in that case. Because you could always have, you could always be building two possibilities that you just end up choosing between based on, like, I really don't know. Yeah. Or even, there's the possibility of having like multiple right wrappers, but that's really not, that's getting theoretical. And so I'm not going to cover it. It's, if it sparks your curiosity, go for it, but it's not something I should cover here. So kind of stemming from that logic, all we should do here is give back the left E. And the reason for that is we're just preserving the error as we continue to run our function. And so, here, really what's happening with applicative when we applicatively apply a function is we are either continuing to propagate an error, or we have a successful case and we're just doing one more step on that successful case to our end output. For example, if we had either some error or, quite literally, let me just write it out, either some error or a form, we might take this form and then do a second step. We could fmap a second step to, make those form elements or inputs pretty, or a certain format or whatever. Something at the kind of, real type level, let's say. Or not type level, but never mind. Just completely ignore what I said there because I said that so poorly. And so, anyways, continuing on, we have more cases here because we could also have left on this side. And so, Yeah, let me just... And I forget how the actual instance is written, so I'm just going to go to it just to... Oh. I am just... Okay. Oh, yeah. So I guess we're saying if we have a left E on the right, on this side, then we actually do not even care. So, like, you know, kind of going through the enumeration of what we could do here, this is what this is saying. This could also be a right X, and we're going to return left E. But since in this case, when we see any pattern where we see left E on the left side of the operator, it does not matter what is on the right side. We're just going to return that left E. So, yeah. Is that actually true for... wait a minute. Oh, okay, it's doing a little trick. So, it's using fmap to simplify things. So, but this would be another valid way to state it that I think is a little bit more clear and less trickery. You know, we could use fmap here to make this a little bit simpler, but I think it's better to just kind of... I don't think there's any harm in having, like, you know, this code here just to elaborate about how it, you know, how each case would work. You know, because here, so yeah, here they weren't unwrapping this second argument because they were saying just fmap the f, and then the fmap would determine if it's a right or left, and then return the left. But I think this is simpler just to, you know, enumerate them out. And that's the goal at the end of the day. So, yeah, so what else is there to say about applicative? I guess, so applicative is pretty useful in terms of parsing. So, let's say you might have a string where, I guess everyone knows JSON, or most people know JSON. Let me just pull it up for the sake of it. Right, and so we could have this is all just going to be text, and yeah, and this text represents a specific thing, and so we might have a parser that tells us how to parse a line, and then another one that tells us how to parse band, and then another one that tells us how to parse class name. And of course, you know, in all these cases, there are arguments as well, like align with this stuff. And so once we've done that, once these individual pieces are parsed, this parser knows nothing about this parser, knows nothing about this parser, knows nothing about this parser. And so one way to put them together is through applicative. And a good use in this case is, there's another good example that might be easier to understand. But well, no, you know what? I'm gonna stick with this one because it's actually it should be pretty easy to understand. And so like let's say I want to call this my rules, and I have a data type rules, which is some align data type, some ban data type, class name, comment, format, and yeah. So I have a parser which is going to get me an align, I have a parser which is going to give me a ban, hopefully not from YouTube. The parser is going to give me a class name, a comment, and a comment format parser. You get the idea. And so So what the usual format for this is so with rules being a data constructor, and so the nice thing about like applicative is it's kind of, it doesn't matter. I can have the same sort of format whether or not I have this many arguments or if I have 7 more arguments, because what the actual format is going to be is that I have rules, which is going to be f-mapped over a line, or over the align parser, which is going to be applicatively applied to the ban parser, and then to the class name parser, and then lastly to the comment format parser. And all of these parsers are going to be of the type parser A, where parser A is going to be applicative and probably a monad as well. There are some parsers that are only applicative, and yeah, and there's reason for that, but so since this is applicative, we can use this applicative function here, and so what this will end up with is, when we run this statement here, which is going to collect the results of all of these different parsers, we're going to end up with a rules parser rules, where this is the data type that gets returned. So that's the actual that's where I've seen applicative get used the most. And we don't know about Monad yet, but almost anything that you do in Monad can be written using applicative. And there, it's not super important. I don't do this. I'm just aware of it and too lazy to take advantage of it. But applicative is generally faster than Monad. And the reason for that is that you allow more room for optimization by the compiler. And even too, you might look at this and say, well, you might realize that align parser obviously is unaffected by how ban parser works. It's unaffected by how class name parser works, and how comment format parser works. And I don't think this would be necessarily true with parsing, and there's a reason for that. But let's say this was instead a bunch of IO actions where we're just gonna put them together like this. And it's just a bunch of different IO actions. Use your imagination. So there's no reason that these need to be run sequentially. These IO actions do not need to be run sequentially, and so you actually do allow the compiler the ability to parallelize your code. Not to be confused with parallelize your code, that would be bad, but parallelize your code. And yeah, and that's pretty cool. So yeah, but there's not too much to say about it. Now, I guess that really, yeah, that brings us to Monad. So Monad. Oh, and actually, my apologies. There's one more thing we have to say about applicative, and that's this function pure. So if we bring up applicative again, we have this function pure, and so it's very simple. You can see that, well, you might be able to read this as, and you'd be right in saying this, if or, in reading it in this way, that it just takes some A and puts it in the context of the F. So, for example, oh my gosh, pure X equals right X in the case of either. And so, obviously pure is an overloaded function, and we can use it anytime we know we're using an applicative. And we can build functions that all it needs to know is that we're dealing with an applicative instance of some kind. It might not know if the applicative instance is either or maybe, and it won't need to in certain cases. And so we have this function pure X, which will construct it wrap that value in the given applicative instance. So yeah, it's just simply, in the case of either, going to wrap it in right. And why do we wrap it in right and not left? Well, that just simply comes down to what the point of either is. We could do anything we want. We could completely rebuild the language and make it completely strange and not useful. I wouldn't even say that. We could just write it however we want. I don't know. You could have your own code base which says that left is the success case, and no one can stop you. But I don't know. You're just weird. Honestly, that's all I gotta say. Good for you though. I mean, stick to the man. But yeah, we just model right to be the success case, and so in the case of where the goal of pure is just to wrap it in some context. It's kind of like an identity function in the sense that it just doesn't really do anything to it. If we all abide by the idea that right is a success case at this current step, and then we can continue on with it, then you should just wrap it in pure. And again, I think another sort of mental thinking thing to think about is input into a program gives output, and this output is really input to some next thing, some next function. And so maybe another, for example, the future is the future right now, but that future will eventually be the present, and any present will eventually be in the past. And so the reason I say that is because I think it helps to think about applicative and monad in particular, where we are just kind of going from through a number of steps, and we're seeing if we are successful at each step, and then if we can move on to the next step. And that's exactly what we're doing. And yeah, and even to now, if you were to like go through the type of what's going on here, like kind of work through the types, and you evaluated this highlighted segment, you would see that rules align, or like it would correspond to this kind of part here, and so what's left to apply is that it's looking for a band, a class name, and a common format. Like for example, if I had, well, you know what, I'm just going to do this. Why not? Oh wait, but it doesn't know what that is. So, okay, I'm just going to pretend these are ints, just so that I don't have to reapply stuff. But if I saw the type of rules with one argument applied, what? Oh, brain fart. Then I would see that it takes one less int. And then if I check the type, check the type of this, and this still applies even though we're kind of working through an applicative context. Yeah, so I guess, what am I saying here? So okay, that was 31 minutes. So I'm going to stop it here, just because I'm doing this as a 3-part series, and yeah, so that's really all there is to say about applicative. It's not that complicated. The number one thing to think about is just when you are thinking about applicative, I would just ask next, like, what applicative is it? Is it either? Is it maybe? Is it IO? Because there is also, the applicative of IO, and, we can see that it's doing the same thing. Like, I could do, for example, get line. This is how I should do this. I should illustrate this example. Get line. Hey you. So I just use applicative to get that done, and that's what's going on. I don't even know. I will say too, I don't know what the applicative instance of IO even looks like. I don't know if that's even like shown anywhere. Maybe I could look into some sort of GHC module, but yeah. So that's definitely all there is to say about applicative. Join me for my next segment, Monads, and I'm going to do this in 2 seconds, but anyways, if you're not joining us for that next segment, happy afternoon, morning, night, out of order, whenever you like to code, blah blah blah, and peace out.